All right, welcome. So in this video I want to continue discussing computational complexity theory. In the last video we defined what computational complexity theory was, and we took a look at our first class of decision problems, P, for deterministic polynomial time. Now in this video I want to continue where we left off and discuss another important class of problems in complexity theory, the class of NP, which stands for non-deterministic polynomial time. So to do that, let's begin by taking a look at the power of non-determinism itself. So I'm going to introduce this with sort of I guess a thought experiment or just sort of a little puzzle here. So imagine you had a friend named Merlin. Merlin claims to be a wizard, a special kind of wizard, a computational wizard, the best kind, that can compute the solution to any problem in a single second of thinking. So, he just means he's fast. He's really fast, and he can solve any problem you want. So pick a hard problem that you might know of, like the traveling salesperson problem, or maybe the knapsack problem, and think, well, that's a pretty hard problem. Imagine a really big instance of it. He claims he can solve that problem in 1 second. So really faster than, say, a modern computer could do it, certainly faster than you could do it on your own in your head. So seems like a good power. Okay, but of course we don't trust Merlin. As far as we know, wizards aren't real, and if they are, they sound like tricksy kind of beings, so we probably shouldn't trust them. I'm certainly not going to trust him with computing something that my life depends on, so I'm going to test Merlin. I'm going to say, all right, Merlin, we'll believe you're a wizard if you can pass some of our tests, some of our computational tests. And so, having just studied some number theory, looking into prime numbers, we've decided, well, maybe we should ask Merlin if he can prove to us that a number is composite or not. And so we head over to Wolfram Alpha. That's at least where I got these numbers. And you grab some numbers, and you say, okay, I've got these special numbers, Merlin. Can you tell me which ones are composite? So I'm going to tell you a secret how I got these numbers. I grabbed a number that was prime. That's where I asked Wolfram Alpha. I said, give me a big prime number. These are pretty big numbers. Let's see here. That's like 1,000, a million, a billion, like 6 billion. That's pretty big. So I grabbed a pretty big prime number out of some list, I'm sure. And then for most prime numbers, most prime numbers, if you add 1 or minus 1, you get an even number. That's definitely not a prime number. That's a composite number. But those ones are easy ones to prove that they're composite. So I wanted ones that are a little bit harder to do. I can tell if a number is even or not with 1 second of thinking. I want something harder than that. So I decided odd numbers only, and so I picked one of these numbers as a prime number. But the other two, I just sort of added 2 or subtracted 2 to the prime number. I can't remember what I did. That created 2 other numbers. I had to quickly check. But for most prime numbers, if you add 2 to it, you don't get another prime number. You usually get a composite number. But these are composite numbers that aren't, or which one's a composite, I'm not sure. I told you the secret. I'm not telling Merlin the secret, but I told you the secret. One of these is prime and the other 2 is composite. And now the test we're giving to Merlin is tell me which is which. Now here's where the tricksy part of wizards comes in. So sorry, we're asking Merlin, we're not at the tricksy part yet. We're asking Merlin here to prove to us the answer. So if he comes and tells us this one's composite, this one's prime, we're not going to trust him. And in fact, whenever he comes and tells us that a number is composite, we're going to say, well, prove it to us by giving us a factor. Now, it's harder to prove something's prime, and I'll get back to that in a second, but when it's composite, we're going to ask Merlin, okay, well, give us a factor of the number. Now the reason we're going to ask him for that is if it really is a factor, we can quickly go grab our calculator and punch it in and see if it's a factor or not. Or If, for that matter, if we don't have a calculator, we can do it by hand. This is an easier step to carry out by hand than, say, finding out if this is a prime number or not, just dividing it by one number. And so we think of that as a simple test that we can perform to see if he's lying. Okay, now this specific test kind of only works for composites. If he tells us it's prime, we're just going to trust him. But if it's composite, we're not going to believe him. Now here's where Merlin's going to come in and try and trick us. He's going to try and tell us that all three of these numbers are composite. He wants us to believe him. But we've told him, no, we're not just going to straight up believe you they're composite. We know one of them's prime, because I told you that that's how I generated it. So we know you're lying on one of them, Merlin. So if you think that these are all composite, then prove it to us. Tell us some factors. So he comes back and says, very well, the first number is divisible by 3, the second is divisible by 7, and the third is divisible by 3. He says very confidently. Maybe he doesn't think that we're going to test him. Well, sure enough, we do, and we run the first number through, and we find out that it's not divisible by 3. So we know he's lied to us on this. Now I need to make an extra comment here. We know he's lied, but that doesn't actually confirm that this is a prime number, other than the extra secret promise I gave you earlier that one of these is prime and the others are not. So the truth is that he gave us the 3 as the possible divisor of this number, but it turns out not to be true. Well, there could have been another one. And we'd have to go and double check that this is actually prime, and we'll do this on the end, or you can take my word for it that it's actually prime. But the other two numbers, he gave us actual factors. So the first one, the second one here, here's its prime factorization there. It is divisible by 7. And the third one is indeed divisible by 3. There's its prime factorization there. So basically the outcome of this experiment is we kind of have to trust Merlin in these two cases where he's given us a proper factor, but in this case I'm not going to trust him. I'm going to assume this was my prime number to begin with. Now he lied to us only because maybe we double check later, or because you trust me. Only that way do we know that this one is a prime number. So do we trust if Merlin is indeed a wizard or not? Well, I don't know. That's up to you. If you ever encounter this friend Merlin who claims they can do this, they're probably just really smart, or maybe they are a wizard. Now, the reason I claim that this Merlin is a wizard is because this power that we're talking about here, the power of basically talking to Merlin about these numbers or whatever problem we're trying to solve, is the power of non-determinism as we imagine it in computational complexity theory. That is, we believe we have this power that we don't really have, but we're going to imagine we have it because it makes some things easier for us. For instance, it makes deciding if a number is composite or not easier for us. This is just a simple example. It's easier to just divide a number by one factor than it is to check to see if this is composite by going through a primality test or some other kind of test. So this implication is that if we did have access to this power, would it actually make it easier for us? Would we actually be able to solve things? At least on the surface here, it looks like the answer is yes. So the sort of first opening question when we present ourselves with this new model of computation, non-determinism, is this more powerful than what we already have, or is it the same power, or maybe less powerful than what we already have? So the process we actually just went through with Merlin was a process of verification. So Merlin made a claim about the output for our decision problem, yes or no, and we wanted to verify that that claim was correct. So we challenged Merlin to give us a proof that his claim was correct. And then we went through a procedure that verified if that proof should be trusted, that is, if it was correct. And the purpose of a verification procedure is hopefully to never be tricked by the wizard. That is, there should be no way that Merlin should be able to convince us to say the wrong answer. So here I've gone ahead to formalize what we, well, let's together sort of formalize what we just did. We were really talking about this problem, which is composites. And you might notice that this problem is actually very similar to the primes problem. It's actually the opposite problem, which we technically call the complement problem, which is any number that we should say yes on, we would say yes on. Any number we should say yes on, sorry, for primes, we would say no on for composites and vice versa. That's what makes them complement problems. And so we're actually going to solve this one because there is an asymmetry to these two problems, something that makes one side a little bit easier than the other, at least from the perspective of verification. So we've shifted gears from the last video to this video into composites, but we basically asked Merlin to convince us that numbers were composite, that is, convince us to say yes. And if he wasn't able to prove it to us, we were just going to say no by default. So we'll assume it's not a composite number you're giving us unless you can prove it to us. So we came up with this verifier. Now this verifier I sort of described, but we can now take a look at it in more detail. In this verifier, let's first of all just see how I've got it set up. It's taking the input to the problem, that's C, okay? But it's taking an extra piece of input as well, which I'm calling W here as well. So this is additional. Now this is going to be a characteristic of verification procedures, which is whenever we create a verification procedure, it will always take the same input that we had for the main problem. If we're coming up with just an algorithm, we just take the normal input, but it always takes an extra piece of input too, and it's sort of up to us to give it a name and decide what we think it is. And so this extra piece of input that we get, we are going to assume that this is whatever Merlin gives us, the wizard. So in our composites, remember, we asked him for a factor. So this is that factor that he's going to give us. And usually we give this a name. And when we were asking for it from Merlin, we asked him for a proof. Prove to us that it's a composite number. So sometimes we call it a proof. Other times it's got other names, so I've sort of highlight these here in case you encountered this in the literature, different names. One other name is a witness. We might say the factor witnesses that the number C is a composite number, or a certificate, as though the factor certifies that this is a composite number. In the same sort of sense that it's a proof, it certifies it. It witnesses it. So all these different names have been given over the history of complexity theory, and because these different names have been introduced in different conventions, people have been raised calling it different things, academically raised that is, you might find different phrases or names for this in the literature. I default usually to proof, but what that means is when I have to give a name for it in my formalization, I'm going to give it a name. Usually I pick P or W or C as the name that I pick for it. Well, in this case, I'd already used C, so I'm going to swap it out and call it W instead. And the other convention I usually use, in this case, I've used a lowercase w. Normally for numbers, we're going to use lowercase, following the convention for most algebra. But say I was going to introduce this as a set or something else where I would normally use a capital letter, I might introduce it here as capital W or capital C or P or A or anything. It could be anything. We just want to highlight it as this extra input for the proof. So now let's think about this. We didn't actually say, how can we make sure we don't get tricked by Merlin? Okay, now I've got spoilers here, so you can probably already see the test we need to do here. But the verifier that we're going to build is going to always have this structure where basically what we're going to do is test, 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 test. If we fail any test, we say no. No, 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 all the way along. But if we passed all the tests, then you've convinced us, we'll say yes, it's composite. Okay. Now here we want to make sure there's no way that Merlin can trick us. Now, I actually want to highlight here, go down to the bottom. This bottom test here is really the one that instinctually we should be feeling in our heart. How do we check to see if this is a factor or not? Well, we should divide it. That's probably what I mostly focused on in the last in the last example when we were treating this informally. We said, well, we'll divide it by this factor and we'll see if it's not an integer. That's what we did to 3. It wasn't an integer, or to that example. We divided it, it was not an integer, and we said, no, it's not. Then you didn't convince us. What are these other tests doing for us? Well, these are all ways that Merlin could subtly trick us if this was the only test we did. So say all we did was divide it. So again, I'm going to give us some examples. Let's say the number we've got here is 7. Okay, and this is just for an example. So 7 is actually not a composite number, obviously. So we should not say yes, we should say no, which means one of our tests should catch it. But let's say we only did this test. We divide C7 by some number, and we see if it's not an integer, then we'll return no. Well, the first thing I could do is I could say, well, I could give C 3.5. Sorry, not C, C is 7. I could give W 3.5. 7 divided by 3.5 is 2. That's an integer, so I should say yes. So how did Merlin trick us here? Well, Merlin tricked us because, wait, the definition of what a factor is isn't just anything that I can divide C by and give me an integer, but it has a specific specific definition, and part of that definition is a factor is an integer. So this first test is important. It's saying, hey, Merlin, whatever you give me, it better be an integer. You're not going to trick me by giving me 3.5s here. Okay. Now the other thing this does for us, which is more of a pragmatic computational observation, is by our first test being, hey, this should be an integer, it rules out that Merlin gives us something bizarre. Merlin could give us anything. We don't do any type checking on this, so this first step really is kind of type checking. Look, Merlin, you should give me an integer. If not, I'm immediately going to say no. If you give me, a real number, I say no. If you give me something that's not a number at all, immediately I say no. Okay, so at this point, if we've passed this first test, we already know, all right, Merlin, haha, you can't trick us that way, you've given me an integer. Now, the next thing is we could go down here. Is there a way that we could Merlin could still trick us if he's restricted to giving us an integer? Well, again, let's go back to C being 7. We could imagine giving 7 itself. 7 divided by 7 is 1, right? Then I would say yes. So we need to remember that factors come in a range. And that range that we should expect, of course, is between 2 and C minus 1, at least we should expect. Remember, we want to rule out the possibility that they can give us a W that is a 1 or equal to C itself. C is always divisible by C, C is always divisible by 1. Remember, that's the definition of a prime number, only divisible by those. So we want to rule those out. So the range that I'm going to pick, the actual change that I'm going to make here is that, so now if you're outside my range, I want to reject you right away. So if you're less than 2, meaning you're 1, or anything else bizarre, I don't want anything else below there. 2 is the smallest, I'll return no. Otherwise, if you're greater than or equal to C, I'm going to say no as well. So these initial tests, I think a little bit more as being kind of type checking tests, and that's the reason why I sort of placed them before the divisibility test, which is really the confirmation that this is indeed a factor. Otherwise, we're just making sure we've got an integer in the appropriate range. Now, additionally, we can tell here, hopefully, well, we're going to try and argue this in a second, but have we got all the tests we need? Is there any way that Merlin can trick us now? Well, the answer to that question is actually no in this case. We'll prove it in a second, but the reason is because we've applied the definition of what a factor is explicitly here. A factor is a number within an integer, rather, within a specific range that divides, that properly divides the number c. So because we've just taken the definition of what a factor is, applied it formally, and made it as a test here, that's exactly what our verifier does. Okay, so I did mention that if we're going to trust this verifier, we need to now prove that it's correct. So let's focus on this. I'm going to start by commenting on an asymmetry that comes with the verifier. And asymmetry meaning the way we treat yes answers and no answers are treated differently here. So first of all, if the input should be accepted, so if we should say yes on C, then we have a pretty strong case, or rather, if we should say yes, then now remember, in this instance, we're testing for composite. So if we should say yes, how would we be able to force ourselves to say yes? Well, then that means there should be some way that I can give you a W that will pass all the tests that are going to catch me and say no, and eventually say yes. So if I am given a composite number, then there should exist some factor that'll pass my test. Well, any factor that will do other than C and 1 and 1. So again, imagine our C is 8, not 7 this time, because that's one we should say no to. But if we have 8, then if we're given 2 or 4, 2 or 4 will pass all of these tests and make us say yes. So that's our condition of correctness if we should say yes. If we should say yes, then there should be some proof that gets us to the yes. Not all of them. On the other hand, if we should say no, then there should not be any proof. The opposite of this claim here is then there should be no proof, W, that will ever bring us to the yes. Meaning, no matter what you give us, we should say no on it. Okay. Again, this is an asymmetry, and the asymmetry can be pretty clear here. If we think of this logically, the is some is an there exists, whereas the is no is there are no. For all, there is not. So there are none. And so we have an existential quantifier and a universal quantifier that arises due to the negation of the existential quantifier above, right? Remember, when you negate a there exists claim, you get a there are none claim. Okay, so when we want to prove this, then we actually want to prove sort of these two branches, and they ultimately we could characterize this as an if and only if statement, and we could state this in this way. We could say we return yes, or we say yes if and only if we should say yes, and that's sort of how I've got it set up here. Our verifier returns yes if and only if we should say yes. Now that's two branches all in one, and maybe I'll capture them right now. When we break these into their conditional statements, we could have if we should say yes, then we do say yes. That's actually going this direction. And then if we do say yes, then we should say yes. That's sort of saying if we got to the end and we arrived at the yes, then that was because this was a composite to begin with. The original direction was saying if this is a composite, then there's a way for us to get to the end and say yes. Now, the reason we need to prove both of those branches is because the one that sort of goes backwards is really saying if this is a prime, then we end up saying no somewhere along the way. We never get to the yes. And so that's making use of the logical idea of a contrapositive. So a contrapositive, if you recall, a contrapositive is where we take a conditional statement like P implies Q and we flip it, but we flip it and negate it. So we turn it around, we now get Q implies P, but I negate both. Okay, so we negate not Q implies not P. Now the power of a contrapositive is the contrapositive always has the same logical value as the original statement. So if you want to prove the original statement, you can prove the contrapositive, and vice versa. So these two statements here I've labeled 1 and 1 here, Roman numeral 1 and 1, are equivalent, logically equivalent. And then the same thing is going to be true here for 2 and 2. And what that means is if we want to prove our procedure is correct, we merely need to prove 1 of 1 and 1 of 2. Doesn't matter which combination we pick. Now, usually I'm gonna pick one strategy or another, whichever one I think feels easiest for me to write the proof. Easiest, not necessarily easy, but maybe most natural in my way that I want to frame it. Now, that might also be the case that for me, the way I frame it might not be the same as you. So if you feel like, hey, I'm going to do yeses in all the way around, I'm going to do yes this way and then yeses back again, that's great. If you want to do no's the whole time, or you want to mix and match, go ahead. Now, I'll show you how I'm going to do it for my proof here. Now I'm going to split these into two proofs, one in one direction, one in the other, and so I'm going to characterize them as lemmas because together the lemmas are going to be a proof of correctness. Okay, so here, to start out, I've got myself my verifier's already started here, but my first lemma, I'm going to say if we should say yes, so if this is a composite number, then we do say yes. We return yes. Okay, I could rewrite this composite number here and say, I could rewrite this lemma, sorry, by saying if C is a composite number, then we say yes, then we return yes. That would be equivalent, but I'm sort of writing it this way so that when we get to other verifiers, we can use the same structure. All right, let's see if we can follow the proof here. Now, well, maybe before we go into the proof, let's remind ourselves, what do we need to prove? So we need to prove that there is some proof that gets us to the yes. Not all of them, just some. So, okay, so let's start out. We're starting out in the case where we should say yes. So what we know is we have a composite. We know it's a composite. So how are we going to argue that we should say yes? Well, if we know it's a composite, there must be a factor. Not just any old factor, but a factor that's an integer that's in the correct range and that divides our composite number. So if we actually are given the factor by our prover, Merlin, whoever it might be, then it should get past all of our tests and get to the end. So that's the argument we're trying to make here. So again, so assume we should say yes. So what do we know about that? That's where we go look up the problem statement. So C has a divisor between 2 and C minus 1. That's the range here. Assume W is this divisor, okay? The word divisor implies the integer part, okay? So as an integer, it passes test 1. This is what I'm calling test 1. And since it is in the right range, it passes the next two tests. And since it is a divisor, we know that it will pass the final test, so we say yes. Okay. All right, so again, this is a little bit verifying what it means to be a factor. Okay. So let's continue. We have the other direction to do. Now, I'm going to assume this is a no and argue that I do say no, as opposed to saying, assume this was a yes, and therefore it must have been a yes. Now, both are fine. And some of us find that backwards argument. I just find it a little less natural. So I want to argue in a direction that's sort of forward. That is, if I should say no, then I will say no. So let's continue in that way. So let's assume we should say no. So now we're given a prime number. Okay. So assume we're given a prime number. Now what we want to argue is that one of our tests catch it. Now there's actually a way we could structure this. Now one way we could say is here's a longer proof, and I'm going to shorten it because we don't need to do the longer proof, but here's a longer proof. We could say, well, we don't know what Merlin's giving us, so we should assume he's giving us anything. Well, first of all, assume he doesn't even give us a integer. Well, if he doesn't give us an integer, then aha, we ruled it out. Okay. Now we also don't know what happened. Now remember, no matter what he gives us, we're supposed to say no. So we're saying, well, if he doesn't give us an integer, we say no. Okay, good. Let's assume he does give us an integer now. So he passes the first test. Well, if he gives us an integer that's too big, we'll say no. So let's assume he gives us an integer that's not too big. Okay, so we've now passed two tests. All right, well, assume he gives us an integer that's not too big, but is also not too small. So if it is too small, we'll say no. So again, we'll pass on again. Let's just say we're now going to say, let's say we've given we've given Merlin the benefit of the doubt. We know we're going to say no if it's not an integer and it's too big or it's too small. So let's assume Merlin's at least trying to trick us, and he's trying to trick us as best as he possibly can. He's going to make sure he gives us an integer. He's going to make sure he gives us one that's not big enough. He's going to make sure he gives us one that's not small enough. So he's going to give us one in the right range. But we know that since this is a prime number, not a composite number, that if Merlin does follow all the rules up till here, gives us an integer in the right range, our number, because it's prime, has no divisors in that range. So we know, we are confident, we say no on the final test. There's no way to get past the final test. Even if you can get past all of our first 3 tests, there is no way to get past the final test. And that's how I like to structure my arguments for my proof, is say, instead of making the longer proof that I just did there, just jumping to the end and saying, let's assume Merlin is as clever as he can be. He tries to pass all the tests. So we'll give him the benefit of the doubt that he passes the first 2, and then we'll say, all right, but if you pass all of the first 3, you're going to fail the last one. Okay, let's see how I put it together. All right, so again, we're going to assume we say no. So that means C has no divisors in this range. The way I phrase that makes it very clear when we get to the end here. So we're going to say, assume W is an integer in this range. So I've assumed the difference between what I've assumed and what I've said here. I've said there's no divisors in this range. So instead here I've assumed W is an integer in this range. So what do we know? We know there are no divisors in this range, right? We know W is an integer in this range, therefore it must not be a divisor. So because it's an integer in the range, it does pass our first 3 tests, but because there are no divisors in this range, we know it's not a divisor, so it fails this last test, and we're going to say no on this last test. Okay, now the way I wrote my test here, I put this as my last test just because I thought it belonged there. I think it's natural this way. I said these are more like type checking. This is sort of the meat of the verifier. So what happens if I didn't put them in this order? I didn't have to put them in this order. I could mix them around. Could I still write my proof? Yes. We could have assumed it divided and assumed it was in range. But if it did divide and it was in range and we knew that our number was prime, then you must have not given us an integer. So we would say no. So which ones we assume you pass and which one you fail on, it doesn't really matter. But I find it's most natural to sort of say, assume we pass the first however many minus 1 there are, and then the last one we always fail on. That's how I like to structure my proofs. Okay, we're not exactly completely done here. We have a little bit more to go, so one last little bit. This idea that we've just come up with here, these verification procedures, I mentioned that this was intended to model non-determinism, and so I'm gonna say here that we can now define our next complexity class, which is NP, which is going to be all decision problems that have polynomial time verification procedures. So the last bit I haven't plugged in there is this polynomial time. Well, I guess I should go each line by line here and say, can we do this in polynomial time? So the first bit, checking if it is an integer or not, that should probably be constant time. Each of these is just a simple integer comparison, so each of these should be constant time as well. So it looks to me like the most expensive thing is doing this integer division. So how long does integer division take? Well, it's comparable to multiplication, which at least using a naive way of doing that is about an n-squared algorithm if you have about n bits. So remember, the number of bits in our input is what we're using, so we have to be careful when we measure our runtime, but that is still polynomial in the number of bits. So we can see that this is polynomial time. So what this means is we've actually just shown, we've proven it correct, we've argued that it's polynomial time, so we've just shown that our problem here, composite, is indeed in the class NP. I want to argue now that The other class we looked at in the last video, P, is actually a subset of NP. Okay, and so we can do that with a quick and easy argument, but I want to maybe, before we get into that argument, just ask ourselves, what do we need to prove here? Well, we need to prove that any algorithm that we have a deterministic algorithm for, sorry, any problem rather, that we have a deterministic algorithm for that runs in polynomial time, we can make one of these verifiers for it that also runs in polynomial time. Now, the sort of clever piece underlying our proof here is basically going to be that every algorithm is already a verifier. It's already a verifier that just ignores Merlin and the proof, doesn't even look at it, just decides if it should say yes or no, and at the end says yes or no. So again, if we have a problem P here, we know if it's in this set P, we know that it has a deterministic algorithm that solves it in polynomial time. So what we're going to do is we're going to take that and create our verifier. We'll create it by, again, ignoring the proof. So whatever input you give us, we just don't even look at it. And then we'll just run the algorithm. If the original algorithm says yes, then we should say yes, so we say yes. And if it says no, then we should say no. So another way of saying that is if the original algorithm says yes, we'll trust whatever Merlin gave us. And if it said no, then we won't trust whatever Merlin gave us. So this new procedure also runs in polynomial time because our original procedure did. And so our problem must be in NP. So what that means is P is in NP. Since we did this for any old problem P, this is a general proof. That means that all of the problems in P are in NP. So P is a subset of NP. So this Venn diagram here sort of depicts that relationship. And that raises sort of two possibilities. Either P is equal to NP, so we have the same class, this collapses, there's only one circle, or this is the true shape, P is properly contained in NP, and there's actually a problem here that exists here that is not in here. Okay. So this actually remains to be an open problem in complexity theory and in computer science. It's probably the biggest open problem in complexity theory and one of the biggest ones in computer science, just because like some other problems in mathematics, it's lingered for a long time with no answer, and we anticipate that we need some clever proof to do this. And by clever, I mean maybe inventing some new mathematics, something that we haven't seen before, to convince us that this is true. Or it might be a problem, or it might be a statement that is just impossible to prove in the sense of sort of a Gödel sentence, a sentence that maybe we can state logically within with our language of logic and math, but which we can't ever prove within the framework of our logic and our math. It's possible that it is sort of an unsolvable theorem, but that doesn't mean it's not worth pursuing. If you want to try and do it, there's a $1 million prize out there for anyone who can successfully solve the problem. And I contend at least that if you did successfully solve this problem, that you could probably earn yourself a PhD at one of your favorite universities with a little bit of extra work. And so I do suggest you put some time into thinking about the problem, how you might approach it, especially if you are in algorithms or mathematics, because you might be the one that has the clever idea that helps us crack it. Really, every year another important problem gets cracked by some new, fresh young mind that's in the field. So I encourage you to work on it. I worked on this problem and a couple other problems myself that are really tough. And now I'm old and I've tried it enough that I've decided that, one, I think I know what the answer is, but two, I don't think I know how to prove it. So that's a good time to give up and go work on something else. So my last little statement here, I say we, I guess I should say I am pretty sure that P is a subset of NP, that there are indeed problems up here that are harder that cannot be solved in polynomial time. But I can't prove that. I just have this sort of intuition that I've built up from years of working on problems, that makes me think that's probably the right answer. Now again, we're going to leave it to someone else to come up with a proof of that, if such a proof could exist. Now this remains an open problem. We want to solve it, but from it has stemmed a lot of other sort of related problems. And so in an attempt to tackle this problem, our complexity theorist researchers have tried to focus in on the class of NP and said, well, look, inside this class we know there are some easy problems that are also NP. There are also some hard ones. Can we find the hardest problem in NP? Assuming there is one, maybe there isn't. We already know there's infinite problems in there, so there might not be the hardest one, just like there's not the biggest number or something like that. But can we find the hardest problem if there is one? And if there isn't one, can we prove that there is no hardest problem in there? So I'm actually going to leave the answer to that question to a future video, not necessarily my next video. What I want to do in my next video, or maybe collection of videos, is I want to practice a little bit with this concept of a verification procedure. Most of us, if we're programmers, if we're already sort of computer scientists, writing algorithms is our bread and butter. That's, writing programs and algorithms that just solve the problem, that's what we do. But writing a verification procedure requires at least a step of abstraction where we're saying, okay, we're not exactly solving the problem, we're given this like proof, this extra thing, and we're just checking to make sure that we're not being tricked. So I'm going to go through a few examples with a couple other problems, other important problems in the study of complexity theory, just to get us warmed up. So that'll be my next couple of videos. All right, thanks for watching, and we'll see you in the next video.